Good morning and afternoon, everybody. My name is Lauren Korshak. I am the translation lead for the Office of Health Equity, and I am very excited about today's presentation. I just wanted to give you all a little bit of background about the Office of Health Equity. It was created in 2012 to ensure that the Veterans Health Administration provides appropriate individualized healthcare to each veteran in a way that eliminates disparate health outcomes and assures health equity. I urge you all to, to visit the Office of Health Equity's website. We're constantly updating it with new information and new publications, and there is a way to join our listserv and to receive emails on all of the things that we're working on. Today's presentation is on reducing racial and ethnic algorithmic bias and ensuring that VA algorithms are fair. And I'd like to go ahead and introduce our speakers. Dr. Suzanne Tamang is a research associate with the Veterans Health Administration, VA Palo Alto. She's also an instructor in the Department of Biomedical Data Science at Stanford University School of Medicine, a research economist with the National Bureau of Economic Review, an intramural investigator at the National Institutes of Health, and the assistant faculty director of data science at the Stanford Center for Population Health Sciences. Dr. Amol Navathe is a staff physician and core investigator at the Center for Health Equity and Research Promotion at the Corporal Michael J. Krennis VA Medical Center in Philadelphia. He is an associate professor of health policy and medicine and a senior fellow at the Leonard Davis Institute for Health Economics at the University of Pennsylvania. Dr. Navathe is also the co-director of the Health Transformation Institute and director of the Payment Insights team, at the University of Pennsylvania. Dr. Ravi Parikh is a staff physician at the Corporal Michael J. Krennis VA Medical Center and an assistant professor in the Department of Medical Ethics and Health Policy and Medicine at the University of Pennsylvania. Dr. Parikh is a practicing oncologist with expertise in delivery system reform and informatics. And so with that, I would like to go ahead and let our first speaker go ahead and begin her presentation.
Everyone, thank you for this opportunity to speak with all of you. Just one point, my affiliations have slightly changed, so just some minor updates. I continue to work with the Department of Veterans Affairs. I'm now based with the Office of Mental Health and Suicide Prevention and have continued working in my Stanford role with the Department of Biomedical Data Science, also with our Center for Population Health Sciences. I'm very excited to present this work with you, and I'll be focusing on ways we can assess racial and ethnic bias in real-world risk prediction models using one of the VA models, specifically STORM, the stratification tool for opioid risk mitigation, as a use case.
Dr. Tamang, you are muted.
Yeah, I'm having a problem moving forward the slide.
So you could just click into the presentation and then use the space bar. Just make sure your space bar is not hovering over the mute button.
Got it. Thank you so much. So algorithmic bias, should we be concerned in the healthcare context? Why? What is it? We've seen it mentioned in, popular media, our scientific publications, and I would say, yes, we should be concerned. We do not see the types of glaring biases around race that have been found in some of the computer visualization tools, mainly around facial recognition. Those have even, resulted in pushback where scientists will no longer continue to work on them. But we've definitely seen a number of compelling examples why we should be concerned, especially in regard to race. And if you haven't seen the paper by Zaid Obermeyer, that is certainly one to, become aware of. Again, we see racial bias, measurable racial bias in our financial risk stratification tools. And more recently, Emma Pearson at Microsoft Research also presented a really compelling case for why we should address some of the racial disparities in knee pain diagnoses. So I think we'll see a growing number of examples, and including this one. And I'll just mention this was joint work with the Stanford Data Science for Social Good program, a group of really talented undergrads and graduate students that worked over the summer about 2 years ago with partners from the VA, specifically where I'm based, the Program Evaluation Resource Center, part of OMHSP, but also our colleagues at the FDA, specifically the Office of Minority Health and Health Equity. So we took on this challenge of how can we begin to measure this in a way. We have many tools in machine learning and affiliated disciplines to start measuring bias, but many of them are not easily understood or intuitive for subject matter experts. And if we really want to get to the phase of measuring and beginning to develop strategies to potentially address the biases that we can measure, it really has to be a joint effort where, say, the algorithmic and technical folks can begin to measure and present the cases, and we can engage subject matter experts in meaningful conversations on how we can potentially address these biases. So we really built on some of the existing frameworks to come up with something more visually driven, and we could engage in more of this joint discussion of how do we measure and then how can we begin to address. So we picked 4 measures to focus on, mainly because of their establishment in existing scientific literature, mainly the medical literature, but also pulling in some measures from more of the computer science literature. So 4 key measures. I am of the philosophy that, not one measure does everything for many different types of purposes. And I think the same can be said for the detection of algorithmic bias in real-world risk prediction models. So first one is the receiver operator characteristic curve. I'll just give a little intuition for what each of these are. And we do see this widely used in health services research, also in medicine. It's created by plotting the true positive rate against the false positive rate at various threshold settings. You see an example of this on the right, really just showing you that purple line would be our perfect classifier there, and that dotted line would be a random classifier. So we really want to get more towards that upper left type of curve. And I'll just mention too, we come from different areas. So many times we're just calling the same thing, but with different, referring to the same thing with different names. So true positive rate, also known as sensitivity, often recall is what is used a lot in, say, natural language processing or in machine learning. Also, it's called the probability of detection. So it may go by different names to you, but fundamentally, we're all talking about the same thing. And our false positive rate, also known as probability of false alarm. This is really just 1 minus the specificity or the recall. And some people will also just describe the ROC curve as a sensitivity or a recall as a function of fallout. So what does this look like? I'll say the first thing we did as a group was we were using de-identified data from PERC. And have to thank Matthew Miller and the various ISOs that helped us to set up this data and compute environment on Stanford through the use of bringing in some de-identified data. But the first thing we did was actually just make sure that we saw the performance of the STORE model that was reported in the paper. So I don't have a slide on that here, but we were able to model the behavior quite closely, and we proceeded from there. So there's a few things to point out here. I'm showing the ROC curve and the area under the ROC curve by race and ethnicity here. And I'm also comparing the in-sample and out-sample fit. So just to give you a little background here, it's on the slides, but each of the lines here, if we look at just the one on the far left, and all of the ones in the smaller quadrants really are set up the same way. But we have our Asian veterans in the light blue. We have our Black veterans in that darker orange, more of a royal blue for the American Indian, and our white veterans are going to be that yellowish line. So this is essentially the ROC curve for each of those subgroups. We see there is some variation, and a few things to point out are, if you move to the right-hand side, the top is our in-sample. So if you look closely, you'll see that the in-sample on the top and the out-sample on the bottom, there is some reduction of performance. You can see that just by visualizing the curves, but also looking at the area under the AUC curves, which is the AUC is noted there. But in a nutshell, we often develop these models, say on the, more of on the same 2 years of data. Say, for example, use 2016 data to predict outcomes in 2017. But in an operation sense, these covariates, or essentially the coefficients, especially if, we'll talk about a regression model, you're going to apply those coefficients to data prospectively. So you have the new observations from, say, 2017, you want to predict these outcomes for 2018. You're still using those coefficients that were trained on the 2016-2017 model. So you're applying these prospectively. And on the right side, you really see how, one, there is variation between race groups, also between Hispanic and non-Hispanic, but you also see changes in these subgroups in their performance as you move to more out-of-sample data. And we didn't do it on future years, but I suspect as we continue to apply them prospectively, we will see more variation, and it isn't necessarily consistent with the same type of variation we saw in the prior year. So, something else as we're thinking of real-world deployment to take into account, it's not just measuring the bias in the, in-sample fit, but thinking about how we're going to use these operationally and moving, prospectively applying these types of coefficients. And I'll just mention one key thing in all of these charts that I'll show, and that is a lot of the ability to predict, with good performance is related to the number of training examples that you have to learn the model. So, our non-Hispanic population at the VA is larger than the Hispanic population. So you will typically see, better fits, and better performance in the subgroups that have, a higher proportion of veterans. So the second one is precision and recall curve. So this is more from, I think increasingly used in health services research, but widely used within computer science and more on information extraction types of performance, NLP. But these precision and recall curves are created by plotting the precision. So we just saw, we saw recall earlier, which was really sensitivity. Precision is also known as a positive predictive value. So I think in some disciplines, that name might, resonate more. And I mentioned here, recall is sensitivity. And we really do want to look at the probability the model will predict all positive cases for the outcome. And I'll just mention one key important factor about precision recall in contrast to ROC. ROCs were really developed in cases where you have balanced sets. So in terms of the outcome, say like 50% positive and 50% negative, they can be really misleading when you have rare outcomes. And these, we call them imbalanced training sets. So here we have precision and recall. I particularly like it in the sense where we do have a rare outcome, and they can be more informative in these prediction scenarios that involve rare binary events. And in a model like STORM, so we're talking about, this is at least in our mock store model that we reproduced at Stanford with DSSG. This was fit to outcomes such as overdose, but also suicide ideation. So again, these are really important events, but they're not highly prevalent. It's important to predict them well, but they don't occur that often. So sometimes a measure like precision and recall, especially the curve and the area under it, can actually be pretty informative. So here, I'm just looking at it here again by race, again with the different colors, and by sex here. So again, there is more variation in the performance for female veterans, likely driven by the small sample sizes again. And you will see that also within the different race classes. So in terms of, say, white veterans, the performance both within gender and also in and out sample is a little more consistent. But you do see more variation in these smaller sample sizes where you do have less training examples for your model to learn from. So again, here, another place where we see algorithmic bias at play, and actually just thinking about what would the ideal curve look like. With the ROC, it was sort of tucked into that upper left corner. Precision recall, you'd want it tucked into that upper right corner. So these events are hard to predict. This performance is particularly, there's room for improvement, but again, these are really hard outcomes to predict, and they are useful for risk stratification. So false negative parity, this one is most commonly used in the algorithmic bias literature, especially coming from computer science. So the false negative rate represents the percentage of true positives that are missed by the prediction model. So you can see why this would be an important measure to include as you're thinking about bias. And false negative parity describes the closeness of this false positive rate across the different subgroups of interest. And just to give you an idea of what this looks like, again, we have this for the various race groups within the VA. For our veterans, the top is the in-sample fit, the bottom is the out-of-sample fit, and here I just have it carved out by different age groups. So under 50, 50 to 65, and over 65. So again, you can observe these visually driven, really adds more to a point of discussion with subject matter experts versus just a table with some summary statistics. And I also think these, visual diagnostics across different measures helps to provide different types of information that should all be contextualized. And we can slice and dice them in various different ways as people see, as is warranted. And I'll just point out on this one, instead of the area under the curves, you actually have, for each of the race groups in the legend, you get it. You see the number of individuals in each subgroup. So, I mentioned too that it really does make a difference how many examples that you have to train from. And although we have rich longitudinal data of a really nice sample size, once we start getting into specific subgroups, one, we definitely see variation in outcomes and how our models are performing. But we have to think about how much of that might be driven by the small sample size issue. If you notice too here with American Indians, under 50, you have about 1,400 individuals. 50 to 65, we have only, less than 2,500 individuals. And we have about 2,100 over 65. So, relative to whites in these age groups, which are almost, essentially for everyone, but under 50, over 100,000, there's much more data to learn from. So the bias can be attributed to various things, whether it's, measurement bias, whether it's related to imbalances in the sample size, or perhaps the actual algorithms themselves. Okay, and then the last one, which I think is probably, if I could say one that people, resonates the most, and probably the most actionable, especially if we think about, opioid risk mitigation, calibration. So calibration is this property. If we assign some group a risk of X, the actual outcome incidence rate should also be X. So for example, if we assign a group of people a risk of 10% of a certain event, say of overdose, the actual overdose suicide-related incidence rate should also be 10%. So here we see just focusing on race in the calibration here, our in sample and our out sample. On the left is the in sample. You can see those predictions are better. I'll just mention the dotted line there would be a perfectly calibrated model. So again, I mentioned like if we predict a risk of 10%, the actual outcome rate would be 10%. Each one of those bars for each line corresponds with a different risk decile. So if you look at the very last bar on each of the lines, that would be the top 10%. So we do see there for many of the subgroups, it's actually, it's going to encompass that dotted line, so our perfect calibration. But when they deviate from that, it is a statistically significant difference. So we do see that performance is degrading as we move out of sample. And actually some of the subgroups, for example, that we under-predicted, we over-predict in the out of sample. This is really just a platform for a set of tools to help identify, explain, and also just continued discussions for drilling down more, thinking about what are the predictors that might be driving this, especially in relation to some of the biases. Are there potential solutions that we can borrow from machine learning or other disciplines on how to potentially mitigate some of the risk we see with more nuanced techniques? So again, and I'll just mention here, the key finding is that we are under predicting risk here for Black veterans. And you see it clearly here more in the out of sample where that orange, sort of darker orange line is the whole bar is away from that, ideal calibration line. And just to, really make this point about what could be driving some of this, of course, there is the bias, there is the methods that you're actually using, but really the landscape of outcomes and who they impact can also change over time. So it really is, important to think about, here, what is going on in the veterans in terms of, the actual outcome rates, and are they differing among different subgroups over time? Because, that can happen as well. And this left chart is more from the CDC. So, everybody here population level, but we do see a sharp increase in drug poisoning rates between 2015 and 2018. And it is, if we look at certain subgroups, for example, one of the relatively large increases is in the Black population for those particular years. So, I did mention that, one of the issues that we measured is this under prediction of risk for Black veterans. And, very well could be, this need to emphasize ongoing calibration of predictive models, particularly when the population risk is evolving rapidly. So, also a need to have timelier data, really catch the dynamics of how the outcome might be changing within the underlying population over time. And just some, in summary, some key conclusions from this. We do observe racial bias and other types related to demographic factors in the STORM algorithm. And there are sets of measures, I just provided 4 of them, that can provide key context, especially to subject matter experts. We did feel the visualization techniques and this ability to provide model diagnostics or more cognitive diagnostics for really probing the models with respect to subgroups, but also over time can convey important information to subject matter experts. And also due to their role in mental health operations, I'll just mention that we are looking to perform these analysis on the actual STORE models and potentially others within the REACH-BEP program to inform strategies for addressing the bias. And we may not have a silver bullet to solve these issues algorithmically, but I'll just mention two key points. One, the scores from these risk models are contextualized in a larger dashboard of factors. So it's not like we have a number and people are taking action on this number. So even if there is some bias in that estimation, there is other context around the risk that can help to potentially mitigate the bias. It's also being grouped into bands such as high, medium, and low. So, we looked at something for the top 10%. And then again, there may be interesting strategies, potentially maybe synthesizing some of the underrepresented subgroups with new data to potentially improve some of the issues that we are measuring. So thank you very much. I'm going to pass the ball over to Ravi, and I look forward to questions in just a bit.
Great, thanks, Suzanne. This is Amol Navathe. So I'm just going to give a couple of introductory remarks, and then Ravi is going to actually take us through the meat of the presentation here. It's a pleasure to be here. We're thankful to Lauren Whitney, Leslie Hausman, and several others who've made our participation here possible in the first place. The work that we're going to present is built on some of the research work that Ravi and I and other investigators that you can see here on this slide have been doing for now a number of years, but very much at the intersection of the clinical work that we do as well. So Ravi and I are both clinicians, and I'm part of a broader work group that focuses on high-risk, high-need populations within the VA, so high-risk, high-need veterans. And so this work really grew out of trying to, is now actually in some sense a decade old, in the idea that how can we use risk scores and predictive tools as a way to actually make healthcare more equitable in the VA. And the CAN score, which is the score that Ravi is going to tell you more about, was actually created specifically for that reason, initially by a team headed by Dr. Stephen Finn. Joe Francis, Tammy Box, and others have also been really instrumental in getting this into operations as well. We actually worked on a research project looking specifically at the CAN score to try to better understand subgroups of CAN score high CAN score veterans to then try to make this data and information more valuable to clinicians when we uncovered, if you will, that there seemed like there might actually be some algorithmic unfairness to African-American veterans specifically. And so I think it's important context for us to understand that the CAN score itself was an advance for equity. And what we are focusing on here is really how can we make it even better, if you will, for equity by mitigating some of the algorithmic idiosyncrasies, if you will. The CAN score was developed largely led by Steve Finn at a time when the data elements available were quite different. For example, race was not reliably available a decade ago. Now, of course, the whole data infrastructure environment has changed. And so this kind of gives us an opportunity to connect clinical operations with research, with other operations, to then look forward and see how we can improve equity. So I just wanted to give a little bit of background there as to kind of how this project came about and where the CAN score has kind of fit into the broader landscape, and I'll hand it over to Ravi.
Thanks, Amol. These are our disclosures, none of which are relevant to the conduct of this research. We're very fortunate to be funded by a VA HSR&D Merit Award, and I just want to emphasize that this is ongoing work that we're going to be presenting today, but that we feel is quite exciting. So our agenda today is going to be split into 4 parts. First, we're going to try to define algorithmic unfairness or go over a couple of definitions of it. Second, we're going to focus on how can we detect unfairness in the VA CAN score, and we'll go over what the VA CAN score is. And third, we're going to try to present some preliminary data on our research about what contributes to unfairness in the CAN score. And then we'll close by detailing a few emerging strategies of how we think we can reduce unfairness in the CAN score I just want to emphasize we have a conceptual understanding of what may be driving, what may be unintentionally driving unfairness, but we're still exploring ways to mitigate it. And so feedback is definitely appreciated there. So let me just start by saying the VA has been at the leading edge of clinical predictive analytics, in the country and arguably in the world. Owing to its robust investment in data infrastructure, the VA has been on the leading edge of developing and implementing analytics in clinical care since 2006, when the VA began to build its corporate data warehouse, which is, as many of you know, a repository for patient-level data aggregated across the VA. It's updated weekly to, algorithms driven from the CDW are updated weekly to reflect changes in status. We've heard about the REACH-VET program from Dr. Tamang's presentation, which focuses on suicide prevention. But the CAN score as well, which focuses on general prediction of hospitalization and death, is also a widely used risk score. So I just want to emphasize that the only reason this work is even potentially feasible is because of the robust and kind of unprecedented investment in infrastructure that the VA has done. The CAN score, the Care Assessment Needs Score, is going to be the algorithm that we're focusing on today. So the CAN score predicts risk of hospitalization and or death for the VA's entire primary care population. Essentially, anyone who sees a primary care physician is included as an observation. One of the unique aspects about the CAN score is that it's widely used. It's accessed, and this is older data, but accessed 4,000 times by 1,200 VA clinicians and health workers each month. It's used in a variety of ways, but ways that we've at least heard across the system that the CAN score could be used is, 1, to create individualized care plans, 2, to make care management referrals, and 3, to determine geographic sites of new healthcare services at the population level. The CAN score is standardized to a percentile risk. So the way that we see output from the CAN score is usually a score from 1 to 99, indicating how high risk someone is in relation to the population of either hospitalization or death. And it's been shown to have a good discrimination or C statistic. The CAN score relies on 6 sort of broad domains of data, one being demographics, things like race, the race doesn't actually factor into the CAN score, but things like location and age, diagnoses like comorbidities, vital signs, medications, laboratory results, and then prior use of health services. And so within each of those domains is a whole number of variables. And as I mentioned, it's updated weekly at the patient level. So, if you were a care manager at the VA, you'd be able to refresh your panel's CAN score and see a ranked list of patients in order of increasing or decreasing CAN. So our goals within this project fits within the broader goal to improve equity in healthcare resource allocation for veterans. And our instrument or mechanism here that we're working with is trying to create a more fair CAN score. So, our sub-objectives are to ensure that the CAN score is promoting equity for racial and ethnic minorities, and 2, to generate an algorithmically fair CAN score with respect to African American race that'll serve as an example for other VA predictive algorithms and even non-VA predictive algorithms. But hopefully we're aiming to yield generalizable methodologies that could be used to address unfairness in the CAN score and other predictive algorithms. So first, let's just start with what is algorithmic unfairness, because I think this has been quite a well-publicized topic that oftentimes is at least to us, was poorly understood before we started delving into this work. So we define algorithm unfairness as answering the question, does an algorithm systematically mischaracterize risk for a certain subgroup of individuals, oftentimes vulnerable subgroups of individuals? Algorithm unfairness has been well characterized even before, well before healthcare predictive algorithms came about in non-clinical fields, things including recidivism in crime, banking loans, and probably most notably facial recognition technology. Unfairness in facial recognition technology has led companies like, IBM and other large companies to remove facial recognition from their portfolio because of this sort of unintentional but pervasive potential to systematically mischaracterize risk. A common theme throughout all algorithm unfairness literature is that African Americans appear to be particularly disadvantaged by algorithm unfairness. And so we focus on African Americans as a particularly vulnerable subgroup and at risk of unfairness in our study. I think another thing, just to set the stage, algorithm fairness is not the same thing as how accurate an algorithm is. So Dr. Tamang went over metrics like the AUC, which could be similar between non-Hispanic white and non-Hispanic black individuals, and so could make it seem like the algorithm is fair when in actuality it's accurate between the two. What really characterizes fairness is whether we're systematically mischaracterizing risk for a certain subgroup of individuals, accounting for all observed characteristics. So if we were able to put an African American in a white individual's shoes, per se, with the same covariates, at least same observed covariates, would an algorithm generate the same score for that African American compared to that white individual? And so commonly used metrics of fairness are things like false negative rate, or how often does a high-risk individual not get flagged by the algorithm. So hopefully with that sort of primer on what algorithm unfairness is, let's focus on can the CAN score be more fair, and is the CAN score, does the CAN score have some elements of unfairness? Our case study here is going to be using the CAN 2.0 score, which is a slightly older version than what's being deployed now. And we're going to be focusing on predictions of mortality only, not hospitalization. And this is going to be based on 2014 data for over 5 million veterans. So we're working with a very large data set here. So the first point the first thing that we did when we were trying to characterize unfairness is just plot where do African American and white individuals, what are their CAN score and what's the distribution of their CAN score? So on the x-axis here, you could see the 1-year mortality CAN score ranging from 0 to 100. And on the y-axis, you can see what percent of a population falls into a certain CAN score bucket. And so overall, the upshot from this slide is that African Americans tend to have lower CAN scores than white individuals, white veterans. You can see that the peak of African American, the most common CAN scores for African Americans usually are, well below 25, whereas there's a more sort of constant distribution of CAN scores for whites. So this is sort of an initial look that sort of hints that there may be some elements to explore for unfairness. So now, in light of that data, when we try to characterize, well, what is unfairness, we want to highlight just an executive summary that our preliminary data suggests that the CAN score, the VA CAN score for 1-year mortality may be algorithmically unfair using a couple common definitions of fairness, notably equality of opportunity and individual fairness. And so we're going to highlight the data that leads us to that conclusion in the next 2 slides. But the important point here is that lower scores for African Americans are potentially not benign. They may, in fact, referrals for and receipt of specific VA services. And so it's really important for us to be rigorous in how we characterize this and whether there is bias, or whether there is unfairness, I should say. So let's focus on the equality of opportunity definition, which essentially is a standard definition of unfairness that tries to answer the question, do African American and white individuals with the same CAN score die at the same rate in the following year? And so what you see on this graph is a dotted line indicating false negative rates, which I defined before as the percentage of the time a high-risk individual is not flagged as high risk by the algorithm. And so what we see here is that across the distribution of different CAN score thresholds, the false negative rate for African Americans tends to be systematically higher than that for white individuals. And so this, in other words, African American veterans are slightly more likely to be falsely classified as low risk, no matter what threshold you use for defining someone as high risk versus low risk. Importantly as well, when you look at the solid lines, which are false positive rates, white individuals tend to have much higher false positive rates than African American individuals, meaning that white individuals are slightly more likely to be falsely classified as high risk and rule in to certain VA-based care management initiatives. So that's one element that we have explored using our data that suggests that the CAN score may have an element of unfairness. The second definition of unfairness that we try to explore is called individual fairness. Do African American and white veterans who are similar on non-race variables have similar CAN scores? And so this is a little bit of a complicated graph, but just to boil it down, what we did here is match Black veterans to selected white veterans based on their number of comorbidities. In essence, we're trying to create a similarly sick population between Black and white veterans. Each dot here in this plot represents a matched strata of African American and white veterans. And so what we see here is that even after matching on someone's sickness level, their comorbidity burden, African Americans tend to have more, so the difference, the plot here, sorry, I should have said this, is on the x-axis is the difference between Black and white mortality CAN scores, so that CAN scores in the negative direction tend to be higher for white individuals, and CAN scores in the positive direction tend to be higher for African American individuals. And on the x-axis, you see differences in actual observed mortality, not the CAN score. And so what we see here is that even when we match on sickness, African Americans still tend to have lower CAN scores than white individuals, or in other words, have a greater proportion of false negatives, indicated by a higher number of plots in the upper left quadrant here. So this would indicate that the CAN score does not fully meet our criterion of individual fairness as well. Also notice that there's not really a consistent pattern of mortality being higher or lower when we match on comorbidities, as the plots tend to sort of average along that middle horizontal line. So I hope that we've presented some pieces of evidence that suggest that using standard definitions of unfairness, the CAN score may have some elements of unfairness. So now we try to answer the question, well, what contributes to this? Well, when you look across the fairness literature, there's a variety of reasons, both having to do with internal data issues, and commonly cited reasons here have to do with class imbalance, which we'll define in a second, measurement error, or maybe we're not measuring the variables correctly, or maybe we're measuring them inaccurately between different races. A labels problem, so perhaps we're selecting biased outcomes here. That's probably not the case in mortality because it's a pretty standard outcome, but it could be the case with other types of outcomes. And then heterogeneity of covariate relationships. So maybe the covariates, how they contribute to an outcome might differ between African Americans and white individuals. So internal data issues may certainly contribute to algorithmic unfairness, and we're going to focus on class imbalance as one potential area. But there are other external data issues as well, meaning things that happen upstream of generating a data set that we use to train an algorithm. Some of those might include omitting certain variables from the data that we're using as part of the CAN score. And another might be unmeasured mediators between a certain, of a certain outcome that we're not accounting for, sort of unmeasured confounders. Other things as well might be rare events, but we're not going to focus on that today. So let's talk about class imbalance. So class imbalance in the statistical literature is defined as when the distribution of a particular class in an algorithm training set isn't equal to another class. So in this case, meaning that underlying CAN scores and underlying different variables contributing to CAN scores might be different between white and African American individuals. What you see here in the table is that there's a number of domains that are quite different between African Americans and whites in the VA population. African Americans tend to have a higher predominance of female veterans. They tend to be younger, and then they tend to have a slightly higher burden of comorbidities. And so, this really matters when we're using kind of a big glob of data to train an algorithm, because we're, in some respects, masking potential heterogeneity in some of these covariate relationships between African Americans and whites. And so what we think here is that systematic racial differences in age and comorbidities could be contributing to unfairness. So let's start with comorbidities. And so as I mentioned, across the age distribution, African Americans tend to have a higher comorbidity burden than white veterans. You can see that pretty clearly by the higher mean number of comorbidities for African Americans indicated in red compared to whites indicated in blue. So one natural question is, well, what if we match individuals based on their coded number of comorbidities? This is sort of similar to the exercise I showed you before. And so, using the individual fairness criterion, we might say that the CAN score is fair if when we match on comorbidities, African American and white veterans have similar CAN scores. And what we see here on this plot is, again, a difference between CAN scores for African Americans and whites on the x-axis, and just a frequency plot on the y-axis, the difference on the x-axis. And so what we see here is that even when we match on comorbidities, mortality tends to be relatively similar between African Americans and whites, observed mortalities. But the CAN score still tends to shift more negatively for African Americans. And so this indicates that maybe there's something other than comorbidities that's contributing to potential unfairness in the CAN score for African Americans. So next we focus on age. And age is really important because, as you can see on the right, which illustrates the coefficients that go into the CAN score model, age is really important, arguably the most heavily weighted covariate in the actual CAN score. And that makes sense. Age is a big predictor of mortality. But across the spectrum, African Americans tend to have a lower age than whites in the VA population. That might be due to a variety of factors. But the average African American veteran is quite a bit younger than the average white veteran. And so lower age of African Americans, you might imagine, could be a large contributor to algorithmic unfairness in the CAN score. And in fact, when we match on age in addition to comorbidities, here we see that the distribution of CAN scores starts to look a lot more similar. And so one sort of big takeaway here could be that age is a potential key driver of unfairness in the VA mortality CAN score. That's at least a working hypothesis that we've been exploring. So now I want to focus on, I hope I've highlighted some areas in internal data issues regarding differences in age that may contribute to unfairness. Another potential as well, and we're sort of in the home stretch of these slides here, so I want to make sure we have time for questions. But another potential is related to external data issues. So the way that the CAN score was generated was that hundreds of thousands of variables in the corporate data warehouse were reduced down to a series of around 300 variables through a process called the factor scan. And then of those, an algorithm was trained that resulted in 36 variables resulting in the currently used CAN model, the CAN 2.5 model. So you can see that there's a big variable drop-off in the number of variables that are being used. And so, like I mentioned, we're using all the same variables to train algorithms between African Americans and whites when we train the CAN score. What we see here is that when we try to fit machine learning models and plot variable importance, or what variables really contribute to a mortality risk score, the variables in a pooled model that includes both African Americans and whites, this is indicated in the leftmost column, the variables that end up being important towards predicting mortality, things like age, statin use, beta blocker use, number of telephonic notes, they end up looking pretty similar for both the pooled model and a model that's trained only on white veterans. When instead we train a model that's specifically on African Americans, the variables that sort of rise to the top in terms of being predictive of mortality often look quite different. And so this suggests that there may be race-specific variable sort of interactions or variable relationships with the overall outcome of mortality that we're not really accounting for, that are potentially being masked in the way that we derive variables for the CAN score and train the CAN score. And so this is a really interesting area that we're still in the process of digging into, using the broader set of variables that those 275 or so variables that not all of which made it into the CAN score. And so this is some data that we hope to have some exciting preliminary data over the next few months. So I want to spend the last 2 or 3 minutes just talking about strategies to ameliorate unfairness. And you know, this again, you know, we're not claiming to have the end-all be-all answer here. This is just some examples using preliminary data from the CAN 2.5 score of ways that we've tried to explore this. So we want to just emphasize that the false negative rate is our metric of interest here. I think I've explained the false negative rate before. It's the percentage of low-risk veterans who end up dying in the next the false negative rate is actually you know, the difference in it's the percentage of high-risk veterans who don't actually this is the correct definition, percent of low-risk veterans who die in the next 12 months. Essentially, you know, veterans who aren't flagged by the CAN score who end up dying. And so a fairer algorithm would have no difference in false negative rates between African Americans and white individuals. And so what we've done here, I won't go through all of these, is we've just explored different statistical techniques to try to mitigate unfairness, essentially using the existing variables that we have. What are different ways that we can manipulate the data, including you know, weighting variables differently, weighting race differently, or creating separate models between different races that might reduce the difference in false negative rates between African Americans and whites. What we found here is that, in general, a lot of our statistical techniques, that these difference in false negative rates still persist. African Americans still have a higher false negative rate. But we have some interesting preliminary data that using more advanced machine learning models might help to reduce some of the false negative rate differences and could be an interesting area to explore. Another area that we haven't started digging into now because we're just aggregating the required number of variables is exploring social determinants of health. The VA has been on the forefront of routinely collecting data related to social determinants of health and social factors that could be contributors to mortality risk and disproportionate contributors to risk for African Americans. We can see hints of this from our own data that we observe. African Americans tend to have a lower enrollment priority. They tend to live in more urban areas. They tend to have higher rates of being unmarried, and they tend to have higher rates of disability, all of which you can imagine as being potential surrogates for adverse social determinants of health. And so in our next iteration of this work, we're actually thinking about using some of the routinely collected social determinants from the corporate data warehouse as additional covariates in our CAN scores based on you know, seminal work from individuals like Blosnich and others to try to improve upon the CAN score and, most importantly, reduce unfairness while still retaining an accurate CAN score. So, you know, I hope that you know, we've kind of given you know a worldview of how we define unfairness and how we might characterize and potentially mitigate unfairness using a representative algorithm at the VA. And you know, we're happy to take any questions, but thank you very much.
Thank you so much for presenting. So we have a few questions lined up. We have a few minutes left, so I'll just try to get through them. So the first question is, it's somewhat long, so bear with me. Again, where is this data coming from? Medical centers, CBOCs, specific communities, and how accurate is the feedback? Are stakeholders well-versed in data collection on all ends? That's part one.
Yeah, it's a great question. I can take a stab at this. So the data itself is coming from it's coming nationally from basically any interaction with the VA system, whether it be in outpatient, inpatient, rehabilitation, any settings that are directly that are direct VA settings, is feeding in data into the corporate data warehouse and is feeding in data you know, into the CAN score. The underlying population, though, are people who have a VA primary care doctor and have a VA primary care appointment. So individuals who aren't seen by a VA PCP over the prior year aren't going to be, part of the cohort that is in the underlying algorithm.
Thank you. And then the second part to this is it seems the driver seems to measure black and white. Should we also measure all veterans, nationalities, example, Asian, Native Americans, and so on?
Yes,
Absolutely.
I think of course. Yes, but again, we have small sample sizes there. Although VA does collect race and ethnicity data, I think much better than, say, other health systems. There are still some issues with measurement, and variation across sites in terms of the fidelity of information. So I think it's key, especially in mental health outcomes where you have specific types of vulnerable populations, say like, American Indians or Pacific Islanders, which, may be particularly vulnerable in some contexts. So I think really focusing on everyone, but again, there's limits to the type of data we have. And again, a lot of this is clinical data warehouse, observational data. So often what we're measuring is just a function of who's coming in for care, what's being diagnosed, versus like the true underlying drivers of some of these phenomenons.
Yeah, this is Amol. I would just add to Dr. Tamang's point. So in the CAN score work specifically, we actually did to some extent look at other factors, other characteristics. So for example, we were worried that there could also potentially be an algorithmic unfairness, if you will, for veterans who reside in rural areas versus urban areas. So we actually looked at a whole slew of factors, in fact, and the one that kind of emerged as the most problematic, if you will, was the African American versus white racial difference. But absolutely, I think you're right that we have to look across a bunch of different characteristics and multiple races and ethnicities as well.
Thank you. And then this question I think came in during Dr. Tamang's presentation. You likely did this already, but what is the difference between in-sample versus out-of-sample data?
So the data is fundamentally the same, but the idea is that you are training this model on, say, 20. We're using initially 2016 data fitted to 2017 outcomes, but similar to CANS or pretty much any real-world risk prediction model, every year model isn't updated and new coefficients are identified. You're essentially using the parameters of an older model and applying it to the newer data. So it's more of like the aging or sentience of your model over time. And that's where, more of that in-sample, out-of-sample distinction comes from. And I think that's probably the best way to think about it. It's very similar to like the idea in machine learning, you have a training set, and also a test set. You can think of it as having your test set from the most recent year of data, and your training set being the historical data.
Great, thank you. So we are just at the top of the hour. We just want to ask our presenters for closing comments.
Oh, I'll just mention too, because I see it in the questions, a few things about social determinants, which, and Ravi and others, mentioned, Amol. I think these are really important to include, but it does seem, there's a wonderful Kaiser paper on essentially using social determinants of health, predicting all-cause mortality. These are likely longer term associations versus, some of the more clinical variables are much stronger predictors. They even sort of, the social determinants will essentially shake out of these models as not being important. So I think, we have to think really holistically about, it's important to measure, it's important to put them in context, but you know, they may not be the strongest drivers in terms of accuracy of models, especially when we're throwing in hundreds of variables or thousands and wanting to distill them down to the most meaningful ones. So I think an important point, but an ongoing and somewhat of an open problem with what to do with them.
Yeah, I'll just close by saying that, I think that these discussions about unfairness are really meant to help improve existing algorithms. I think that the VA is really to be commended for creating an accurate algorithm being actually used to help improve care delivery. I think that the unfairness question is something that has really come on the scene over the past 2 to 3 years when it comes to clinical predictive models. And so, we're, just like the VA, has been on the forefront of creating these. I think the VA has really been on the forefront of trying to, improve them and improve, potential unfairness in the algorithms. And so I think that's really to be commended, and we're excited to keep moving with this work, not only related to the CAN score, but other algorithms as well.
Dr. Navathe?
Yeah, just noting that we're over time. So I agree with the comments. I think, as Ravi and Dr. Tamang have highlighted, I think the VA is very well positioned to make strides in this area, perhaps beyond any other health system. And so I think that's very exciting. As I mentioned, I think it seems like, when we compare to some of the work that's been done outside the VA that Dr. Tamang referenced, the Ziad Obermeyer science work, the degree or the magnitude, if you will, of the unfairness here is considerably smaller. So I think we still view this as, really positive incremental steps towards getting to a more equitable health system.